This is section 8.6, Numerical Integration. This is a review, at least in part, of things that you learned in Calculus 1 about what we did to estimate the area under a curve, for example, using rectangles. And why would we need to go back to that? Well, for one reason, we know that the fundamental theorem of calculus relies on our being able to integrate this function f of x, find its antiderivative, and evaluate it from a to b by substitution of the upper limit into the antiderivative minus the antiderivative evaluated at the lower limit. But all of that hinges on the fact that we need to be able to find an antiderivative of f called capital F. And sometimes that is impossible. You may not be able to find an antiderivative for some function. There's many of these listed on the third screen of the PowerPoint presentation, that there is no closed form for an antiderivative of them. So the best we could do would be to estimate as you started out doing. What we're going to do, though, to make this a little bit more interesting is we're not going to stick with just the rectangles. I mean, you will see some problems like that, but you've done that before, so I'm not too worried about your ability to handle that. What I'd like to do is show you a few more techniques of approximation for the area under a curve, which is the simplest application. From x equals a to b. So we could do rectangles, of course, but I'm going to posit another idea. Let's say that we created 4 subintervals, and the y values at each of those x values and the y value at the endpoints are important. Now it looks like, well, those are supposed to be equally subdivided, but I don't think my drawing was quite perfect for that vertical line at B, but nevertheless. So instead of using a rectangle, which would be, flat at the top, horizontal at the top, what I'm going to propose is that we instead connect those dots with straight pieces. And of course, if you are following the drawing I'm making, those straight pieces are actually pretty good approximations of the curve, way better than a horizontal top. And of course, what's created is a bunch of trapezoids. Remember, the definition of a trapezoid is it's a quadrilateral where exactly one pair of sides of the trapezoid are parallel, and those are called the bases. So I guess we could call this one base 1 and this one base 2. And the distance between them, which can be measured anywhere, is called the height of the trapezoid. And so again, we're going to have a simple figure whose formula for calculating, in this case area, is easy. And the formula for the area of a trapezoid is base 1 plus base 2 times the height of the trapezoid, all divided by 2. Now, I know that a lot of you, when you think of trapezoid, you think of all the pictures you saw before now, and they probably all looked like this, so that the bases were horizontal. And that's what you're used to seeing, and I understand that, of course. But you need to realize that that can be oriented in any direction. And in this particular case, the case that we're dealing with over here, that's what we're going to be dealing with, is the bases are vertical. and parallel to each other. And so let's say we were doing the first trapezoid. The x sub 0 is another name for a, and we'd call this x sub 1. And of course the base values, the lengths of those bases, is the y value evaluated at each of those x's. So base 1, for example, is f of x sub 1, and base 2 is f of x sub 2. And so what we'll have is, for this one first trapezoid, the area of that trapezoid will be f of x sub 1, that's base 1, plus f of x sub 2, that's base 2. Then we'll multiply that sum by the height of the trapezoid. The height, by the way, is our old friend delta x. So delta x, all divided by 2. And that's always a 2 in this formula. Okay, so that's the area of one trapezoid. Then if delta x is consistent, always the same width, and in fact the general idea still that you learned in Cal 1 is that delta x is always b minus a, the total width of the interval, divided by n, the number of subdivisions. That makes them all equally wide. And that makes our calculation easier because if we try to generalize this a bit, trying to make this string mark I made go away, and it's not cooperating. There we go. What we're going to end up doing to get the area under that curve in an approximate way is to sum all such trapezoids from the first to the nth, and the 2 is a constant and the delta x is a constant. So I'm going to pull those out in front, delta x over 2, and we'll be adding f of x sub I minus. Oh, you know, I just found a mistake in what I wrote up there. Sorry, I let myself get distracted, and this bothered me. We were doing what we ended up doing with f of x sub 1 and f of x sub 2, we actually did the second trapezoid. So I know what I need to fix is we're not doing the first trapezoid. Let's just say we're doing the second one. So let me check that that's the one we're actually doing. Okay, let me see if I can fix that. Okay, so this is the one we're doing. But in general, it's going to be f of x sub I minus f of x sub I minus 1. And I said minus and it's plus. I apologize. I was thinking of the I minus 1 and put the subtraction in the wrong place. And that's what we'll end up doing. And as it turns out, this is not a formula that we're going to go to an integral with, because what we're assuming is that, we could if the function f of x had an antiderivative. This would end up giving us basically the same formula we already have for the area under a curve. That's not what we're doing here. N is not going to go to infinity. It'll be, for most problems, relatively small numbers like 4 or 6 or 8 or 9 or 10 or something like that that you have to deal with. But that's what the formula looks like. And so if we expand that a bit, I'll have a common delta x over 2. And we'll have f of x sub 1 plus, oh, actually, let me start with 0. I want to switch the order of these. I just decided. Not that it matters because we're adding, it does, no big deal. F of x sub 0 plus f of x sub 1 is from the first trapezoid plus f of x sub 1 plus f of x sub 2. So keep in mind what we're doing is we're adding the bases b1 and b2 for each trapezoid. We are multiplying by h, the delta x, and dividing by 2, but we do that every time, so I pulled those out as common factors. And let me write one more pair, or maybe 2. So this will be f of x sub 2. We're now on the third one. Plus f of x sub 3 plus dot dot dot, and then we'll have f of x sub n minus 1 and f of x sub n, the last one. Okay. Now, you might notice that the f of x sub 1, for example, appears twice, as does f of x sub 2. It appears twice. And that makes sense because if you're looking at the first and second trapezoid, the left side f of x sub 0 is used once. The left side is used the one time. And doing the first trapezoid, the right side is used once. And then when you go to the second trapezoid, that side you've already used once is used again because it's now the left side of the second trapezoid. And we'll use the right side of the second trapezoid to get the second base. And then we'll go to the third trapezoid and we'll use the left side and then the right side again. So for all of the interior ones, they're all used twice. The first function output, the first y value is used only once, and the ending one, this is x sub n, where b is, and it will only be used once. So the ends are used once each, but all of the interior ones are used twice each. And so that leads us to say that in a more compact form, this will be what we do every time we do a trapezoidal rule. We'll use the first x values, y value once, the second y value for the second x we'll use twice, and for f of x sub 2, we'll use it twice. In fact, we'll keep using each of them twice until the penultimate one, which is used twice. The second to last one is used twice still. That's the last time something's used twice. And then the very last one, the very last x, x sub n, which corresponds to b, that would be used just once. And so what I've just written, this line right here, is the trapezoidal rule. Assuming delta x is the same value for every subinterval, this is a formula that you can use to approximate the area under the curve from A to B, which would be from x sub naught to x sub n, with n subintervals being used. And of course, what that is approximating is the actual area under f of x from A to B. And again, the reason we're doing this is we're pretending like f of x is some function for which we cannot find an antiderivative. And the only way we could get an idea of what that area is with an approximation technique. Okay, so that's called the trapezoidal rule. They write it slightly differently in the book, and that's fine. If you want to learn their way, this is how I always learned it and memorized it. So you can use they use, instead of delta x over 2, is they use b minus a over 2n, which of course is just substituting for delta x with b minus a over n. So that's really no big deal how you do that. So I'm going to use this, but if you prefer the other way, just go ahead and do that. I don't have a problem with it. So, oops. I do have a problem with it when I don't pay attention and copy down the problem incorrectly. That's not good. Okay, we're going to use the trapezoidal rule to approximate the area under f of x equals sine of x from 0 to pi dx. Now, of course, we know how to do this one exactly. So this is not the point, is that we're trying to make it harder. What I'm doing this with a known function for, the reason I'm doing this is that so we have a means of checking how good of an approximation we're getting. So that's going to be the big idea with this one, with a known function whose antiderivative is known. All right, so we're going to do this problem twice. Once where n is 4, and then again where n is 8, according to the directions. That's what we're going to do. And I believe I provided pictures of that. I'm not going to try to draw good pictures of that because I'm pretty sure mine would not look that good. So the first thing I'm going to do is I'm going to calculate delta x for n equals 4. So b is pi minus a is 0 over 4. So my integral, using my first approximation with 4 subintervals, of the area under sine of x from x equals 0 to x equals pi will be, again, approximately equal to, I guess I could have written what this simplified to be, pi over 4. That will be pi over 4, that's my delta x, divided by 2 times f of 0, the first x value is 0 because we're starting at a. Then we're going to move for x values pi over 4 to the right of that because our delta x is pi over 4. So we're going to have 2 of f of 0 plus pi over 4 is pi over 4. Then we're going to move pi over 4 to the right again. Pi over 4 plus pi over 4 is pi over 2. So we'll have 2 of the function outputs of pi over 2. Then move another pi over 4. That was 2 pi over 4, so we're now at 3 pi over 4. And when I move pi over 4 to the right, from 3 pi over 4, I end up at pi, which is my last value. That's my b, so keep in mind that that one you only use once. I have a feeling that I will probably mess up at least once and write a 2 in front of this when I'm adding and not paying attention to b, and then I'll look back and look at what b is and go, oh, yeah, that's the last one. Oh, erase that 2. Oops. And that may happen to you too, so don't despair. You just get in a rhythm and you're just adding pi over 4 and pi over 4 and pi over 4 to calculate your x's over and over again, and you kind of get sidetracked. All right, so this is going to be pi over 8. Sine of 0 is 0. Sine of pi over 4 is square root of 2 over 2. Sine of pi over 2 is 1. Sine of 3 pi over 4 is square root of 2 over 2. And sine of pi is 0. Okay, you do all of that arithmetic, and you should get pi times, pi plus pi square roots of 2. I was trying to decide if I wanted to factor out that pi or not, and I decided not to. All over 4. Okay, and then for comparison's sake, I want to find a decimal approximation for that so that we'll have a thing to compare to. So correct to 3 decimal places, this is 1.896 approximately. Okay, now let's do 8. Delta x this time will be b, which is still pi, minus a, which is still 0, over n, which is this time now 8. So pi over 8 is what delta x is. And so the integral from 0 to pi of sine of x dx will be pi over 8 divided by 2 times f of 0. Now we're going to be doubling all the middle ones, so double f of, now we're moving pi over 8, 0 plus pi over 8 is pi over 8. And then pi over 8 plus pi over 8 is pi over 4. Pi over 4 plus, whoops, I forgot to write the 2. Pi over 4 plus pi over 8 is 3 pi over 8. Pi over 8 plus pi over 8 is pi over 2. So we're halfway done, right? Pi over 2 plus pi over 8 is 5 pi over 8. You see why you don't really want to do this for huge values of n, right? This is already a lot. Okay, 6 pi over 8 would be 3 pi over 4. I think I can get a resounding yes sir for that one. Okay, the next one will be 7 pi over 8. The next one will be 7 pi over 8 plus pi over 8 is 8 pi over 8, which is pi, and that's our ending one. And the ending one, we use it only once. Okay. So the odd multiples of pi over 8 are not values that I have memorized. And so I'm not going to worry about an exact expression this time. I mean, you can get exact expressions for some of those that are like square root of 2 over 2 and things like that you know. But some of it you can't. I'm not going to worry about that. What I really want to focus on is type all that into your calculator. Okay, that's going to take you some time, so pause this and do that. You will probably want to think of that as pi over 16 times that sum of things. At any rate, once you've typed this in your calculator, and that's good practice, realizing just how much you don't want to type that many things. Luckily, it's just a simple function like sine of x. If it were something really complicated, you would want to have a shortcut way of doing that, which if you ask me in class, I'd be happy to show you a little bit of a shortcut on how to do this in a calculator. So it's not quite as painful. It's still not fun, but it's not as painful perhaps as your typing is going to be if you type this one in. So go ahead and type that in, and you should get 1.974 for this approximation. Okay, so let's do the actual answer, because we can actually check and see how well we did. The antiderivative of sine of x is negative cosine x. Which we'll evaluate from 0 to pi. So we'll have negative cosine of pi minus negative cosine of 0. Cosine of pi is negative 1. The opposite of negative 1 is 1. Minus a negative becomes plus, and cosine of 0 is 1. And so the actual answer is 2. So with 8 trapezoids, we got 1.974. That's a pretty close approximation of 2. And of course 1.896 wasn't bad with only 4 trapezoids. Still not bad. And of course the more trapezoids you use, the bigger n is, the closer you'll get to 2. And of course that's the idea of if we make it infinitely many trapezoids, it would actually come out to be 2, as we know. So what this is supposed to do is give you confidence that if you use 4, 8, 10, whatever trapezoids, you should be getting a pretty good approximation of the actual integral value. Okay, now the next one, I'm not going to go through all the theory of it. I'm just going to present you the kind of the ending of it. And if you want to read about how this is developed, that's great. Have at it. Simpsons Rule. Just so you have an idea of something that's used in this, so that you understand it, is that if we have, let me go ahead and draw a function. Oh wait, I don't like that function. Let me try another one. We have some function like this, f of x, and I'm going to have some really big subintervals here. And I'm going to assume that they're equally wide, although I don't think I drew them equally wide. Let's say delta x is always the same, no matter what. So no subscripts to say it's the width for the first one or the second width for that delta x sub 2 and things like that. These are all the same. So again, we'll be using delta x is b minus a over n. That won't change. Now, I picked on 2 of them because this technique needs 3 points. You know, like the trapezoid needed 2. 1 here and 1 there, and then draw the line segment in between. This technique requires 3. And what we're going to be doing here with 3 points is, you know, you can find the equation of a quadratic function if you know 3 points. Because if you are thinking about it, you'll have 3 unknowns, a, b, and c. And so with any 3 points that are known to be on a parabola, you can find its equation by using that formula for each ordered pair and create a system of equations and solve that system for a, b, and c, and those will be the coefficients of your quadratic polynomial. And what we're going to do here is we're going to find the equation of a parabola, and I'm going to assume that I could draw a pretty good parabola that goes through those points. Pretend like that's perfectly drawn. Thank you very much. And the idea is that a curve can approximate a curve better than any straight thing can. So this should be a better approximation than the trapezoids. And because we're using two subintervals, we need pairs of these to be thought of at a time. And so that's why one of the things that is going to be true is that n must be even so that you can pair things up. Now, every problem they're going to give you, n will be even. No worries. But if you encountered having to do this on your own at some point with your own problem, then you would want to make sure that n is even if you want to use Simpsons Rule. And again, that's assuming you don't know how to anti-differentiate your function. Otherwise, you would just use the fundamental theorem of calculus, like we always have. Okay, so as that turns out, and again, I'm not going to go into the theory much, but you end up using, for this pair of things, you use the left one once, the middle one 4 times, and the last one once. Okay? Then, if you have another pair, I'm not going to extend the function. I'm just going to pretend like it goes to here. Wow, that's pretty bad. Let me try to make them at least appear to be equally wide intervals. Okay? And so for this pair, you would use this one once, this one 4 times, and this one once. And so if you notice, this one, an interior one that would have been used once, it's used once for what's on its left, the green, and used once for the pair on the right, the pink. And so that one is used for a total of 2 times. So what happens in this formula is that you have this alternation of 2 of them. Well, so you start with one of them. So this leftmost one will be used just once, this one right here. Then it'll be 4, then 2, then 4, then 2, then 4, then 2, then 4, then 2, until the penultimate one will be 4, like this one here. This one, if we only had these 4 subintervals, the second to last one would be used 4 times, and the very last one once. And so it starts 1, then goes 40, 40, 40, 40, 40, 4, ends with a 4 before the last one. And that's what Simpsons Rule will look like. So this is Simpsons Rule right here, that if we need to approximate the definite integral of f of x from x equals a to x equals b, especially if we do not know its antiderivative or how to find its antiderivative at all, then this will end up being delta x over 3. And again, if you went through the theory of it, you would figure out where that 3 came from. And I'm not that worried about it. This is just memorize it. You know, sorry to say that, but this is one of those where I don't want to spend the time developing the idea. So we'll use the first y value for f of x sub 0 once, the next one 4 times, the one after that twice, the one after that 4 times, then twice, then 4 times, then twice, then 4 times, twice, and 4 times, etc. So you have to know that that's the pattern, alternating between 4 and 2 for all the interior ones, until the one that's third from the end, second from the end, sorry, will be used twice. The penultimate one would be used 4 times. Okay, second to last one's used 4 times. And the last one, x sub n, is used just once. And that's Simpsons Rule for approximating a definite integral with n subintervals where n is an even number and delta x is b minus a over n. Okay, and this too, if we made the number of subintervals n go to infinity, we would actually get the definite integral. And I just realized I made a mistake here, so I need to fix that. That's not what the definite integral is. That's what it is approximately. So I'm going to go back and look at the other ones that I wrote, make sure that I wrote approximately when that's all it's giving us is the approximate value, not the exact value. Okay, now this is exact here where we were doing the antiderivative. Approximately, approximately. This equal sign right here is okay because I'm saying that it equals the line above it. It's exactly the same as the line above it, just simplified some. So that's not a false equal sign. But the definite integral is approximated by this formula to the right, pi over 4 over 2, etc. So yes, I think I got everything right as far as equals and approximately equals to. I think we're good. Okay, so let's do the same value for which we already know the actual answer is supposed to be 2. And to compare trapezoids to Simpsons Rule, we're going to do the exact same problem with n equals 4 and n equals 8 so that we can compare how well those did compared to each other. All right, so when n is 4, delta x will be pi minus 0 over 4. No big surprise, it's the same delta x we did before. And again, that makes it so that we're comparing like things. So this will be the integral we're trying to approximate. And it will be delta x, which is pi over 4. For Simpsons, we divide by 3. Trapezoids, we divide by 2. And so that may help you, make it, it will make a difference in your answers if you mix those up, so be really careful. Okay, so this will be f of 0 is our first x. Then we're going to have 4 of the next one. And 0 plus pi over 4 means our next x is pi over 4. Then we'll have 2 of the next thing. Pi over 4 plus pi over 4 is pi over 2. Then 4 of the next thing. Pi over 2 plus pi over 4 is 3 pi over 4. And then that plus pi over 4 is pi, which is our last one, and it's used just once. Okay, so that's equal to pi over 12. Sine of 0 is 0, plus 4 times sine of pi over 4 is square root of 2 over 2. Sine of pi over 2 is 1. Sine of 3 pi over 4 is square root of 2 over 2. And sine of pi is 0. that turns out to be approximately 2.005. Now, compare this to the trapezoidal answer with n equal to 4, and that was 1.896. Which one's closer to 2? Well, 1.896 is 0.104 away, right? Did I do the arithmetic correctly? So the trapezoidal answer is 0.104 off, and how far is this one off? It's 0.005 off from 2. So with the same number of subdivisions, we're way closer with Simpsons Rule than we are with the Trapezoidal Rule. Okay, so that's a comparison I wanted to make, is that that would give us a little bit better answer. Okay, with delta x equal to pi over 8 when n is 4. We already went through that calculation, so I'm just going to go through it fast. And this with 8, with n equals 8, this is going to be pi over 8 divided by 3 times f of 0 plus 4 f of pi over 8 plus 2 f of pi over 4 plus 4 f of 3 pi over 8 plus 2 f of pi over 2 plus 4 f of 5 pi over 8 plus 2 f of 3 pi over 4 plus 4 f of 7 pi over 8 plus a single f of pi. So again, this would be a good one for you to type in your calculator. So pause and see what you get and compare it with this answer. And you should get approximately 2.00003. That's 0.0003 off from being the correct answer too. And what was that for the trapezoids with 8? Gotta look back and see. That was the trapezoidal answer was 1.974, which is 0.0 0.26. I think I did the arithmetic correctly there. So that's way closer with Simpsons Rule than with trapezoids. Now, trapezoids wasn't bad. I'm not saying it's a bad idea, but Simpsons, generally speaking, will get you way closer to the correct answer than trapezoids will. Okay, so this error, this how much we're away from the correct answer, we're not always going to be able to find exactly what that error is because we won't be able to compare it to the correct answer of 2, which is what we've been working with is one that we could anti-differentiate and use the fundamental theorem of calculus to calculate the exact answer of 2. Since we can't always do that, we're going to want to find an error bound for the trapezoidal rule and for Simpsons rule. And so if you look at theorem 8.6, assuming f has a continuous second derivative on the interval from a to b, then the error e in approximating the definite integral of f of x from a to b by the trapezoidal rule is going to be the error, or the absolute value of your error, will be less than or equal to b minus a cubed over 12n squared times the maximum value of the absolute value of the second derivative of f of x on the interval from a to b. Don't memorize that. If you need to, you'll be substituting in b and a and n, and you'll have to calculate the absolute value of the second derivative and find out what its maximum value is on the interval from a to b, and then put it into that formula. And then for Simpsons rule, assuming we do have a continuous fourth derivative on a to b, then that error e in using the error in approximating the actual definite integral from a to b of f of x dx will be, its absolute value will be less than or equal to b minus a to the fifth over 180n to the fourth times the maximum value of the absolute value of the fourth derivative of f on the interval from a to b. Okay. So, in general, when using an approximation, we can think of that error e as the difference between the actual answer and the approximation. So like that 0.0003, I got that by taking 2.0003 minus 2. I just subtracted those two. That's how far they are away from each other. That theorem 8.6 states that the errors generated by the trapezoidal rule and Simpsons rule have upper bounds, dependent on the extreme values of the second and fourth derivatives respectively in the interval from a to b. So we're only able to approximate how far off we are using those rules. We can't find the actual error unless we can anti-differentiate f of x and get its antiderivative and use the fundamental theorem of calculus, like we did with our example of sine of x. And what we can do is we can decrease the error by making n bigger and bigger. Because as n gets bigger and bigger, both those formulas you're dividing by a power of n. And so the bigger number you divide by, the smaller the answer will be. So you can make the error less than a small value if n is really big. Okay. So let's look at this example, example 3. Determine a value of n such that the trapezoidal rule will approximate the value of the integral from 0 to 1 of the square root of 1 plus x squared. And again, we're pretending like we cannot anti-differentiate this to find its value. We want the error that's less than or equal to uh, 0.01. Okay, so we're going to let f of x be our function. And again, we're pretending like we have no idea how to find its antiderivative. But we should be able to find its derivative. No big deal. So, of course, for derivative purposes, we don't like radicals. We'll rewrite that as a power. So that binomial to the 1/2. So the first derivative is 1/2 times the base, 1 plus x squared, to the reduced by 1 power, so negative 1/2. And because of the chain rule, we then have to multiply by the derivative of the inside function. The derivative of 1 plus x squared is 2x. And that simplifies to be x 1 plus x squared to the negative 1/2. Okay, we are using trapezoidal rule. I forgot to write that down. And so if it's trapezoidal, that means that we need the second derivative. If you look at that formula again, that theorem, to get that formula, that means we need the second derivative. If it were Simpsons, we'd be finding the fourth derivative instead. Okay, so the derivative of our first derivative is the product rule that will be employed. So first function times the derivative of the second. So we're going to use that general power rule. Oops, forgot to write the negative. That general power rule. Don't forget the chain rule. Okay, so that's first times the derivative of the second plus the second times the derivative of the first, and the derivative of x, of course, is just 1. And so this ends up being negative x squared 1 plus x squared to the negative 3/2 plus 1 plus x squared to the negative 1/2. Okay, so then what we want to find is the maximum value of the absolute value of the second derivative function on the interval from a to b, and since we're integrating from 0 to 1, that's from 0 to 1. Okay, so that maximum value, if you graph that second derivative function, so I'm going to pick up my calculator and graph it. I'll graph the opposite of x squared multiplied by the quantity 1 plus x squared. That quantity raised to the negative 3/2 plus 1 plus x squared raised to the negative 1/2. Okay, and I can graph it in any window I want, but I'm specifically going to look with a window from x equals 0 to x equals 1. So I'm not distracted by anything outside of that window. As far as the y's are concerned, I'm going to make a guess. I'm going to go from negative 2 to positive 2, and if I can't see this thing peaking out, then I'll, topping out at some value, I'll fix that. Oh, and what I forgot to do. So if you would do this too, since I forgot it, I guess that's a good idea. We really want the absolute value of that function. So I'm going to go down to y2. I'm not going to destroy what's in y1 because I typed all that. It took a while and I don't want to mess it up. So I'm going to hit math. In y2, I'm going to hit math. Go over to the right one to the number. NUM subcategory. The very first option is ABS, which is absolute value of. Then you want to type in y sub 1. So to do that, if you have the new operating system, hit alpha trace and just hit enter because y1 is your first option. If you don't have the new operating system, what you'll have to do is once you have the absolute value left parenthesis, you'll have to hit vars, then move over to the right to yvars, then choose function, the first option, and then choose y1, which is the first option. Okay? So then go up 1, and that'll put you back in the line where y sub 1 is. Left arrow over to the y1 equals, get on top of that equal sign and hit enter. And notice it's turned off. It's not gone, but it won't graph it. Okay? So y1 should have an equal sign that does not have a black box around it, and y2 should have a black box. Anyway, I'm going to hit graph and see what happens. It looks like it starts out at 1 and then just goes down. So I'm going to claim, and you could have your calculator actually find this for you, but I'm going to claim that that maximum value happens when x is 0 with a value of 1. Okay? So now that we have that maximum value of 1, we're ready to do the answer here. So the error, which is, according to the formula, going to be less than or equal to b, which is 1, minus a, which is 0, quantity cubed, divided by 12n squared. And see, what we're doing is we're solving for n, so it's still a variable. So just 12n squared times that maximum value that we just found on the interval from 0 to 1 for the second derivative, and that's 1. And we want that to be less than or equal to 0.001, aka 1/100th. And solve for n. Of course, 1 minus 0 is 1, 1 cubed is 1. So this left-hand side simplifies to be 1 over 12n squared. Then to solve for n, I'm going to take the reciprocal of both sides to get the n in the numerator. And the reciprocal of the left side gives me 12n squared. The reciprocal of the right side gives me 100. And when you take the reciprocal of both sides of an inequality, it changes the direction of the inequality. Then I would divide both sides by 12. Since I'm dividing by a positive, it'll still be greater than or equal to. That ends up being 25/3. And then I'm going to take the square root of both sides, which will not affect the direction of the inequality. And then in decimal form, that is about 2.89. So remembering that n is a number of subintervals, it has to be a whole number. And what's the smallest whole number that makes that true? It's 3. Choose n equals 3. And usually you want the smallest viable answer because the industrial application of this would be you run a process that costs money, and every time you run the process you have to pay workers and electricity and whatever else is involved. And so you want to find out the smallest number of times you have to do this process in order to get an error less than something. So you've got a tolerance that you're given for making some product, and if you do this particular process 3 times, your answer will have an error less than 1/100th, which is your tolerance, you know, if it's for an industrial application. And so you would choose 3, not 17, because obviously with 17 you're going to have a lot of accuracy, but it's going to cost you a lot of money. So pick the smallest viable n is kind of the idea here. Okay, and so then if you use the trapezoidal rule, this integral would be delta x. Oh, and by the way, if it were Simpsons, the answer couldn't be an odd number. It'd have to be an even number. So if this had been a Simpsons problem and you said n is greater than or equal to 2.89, you'd have to go to 4 because it has to be an even number. So I just thought I'd mention that before I forgot. Okay, b is 1 minus a is 0 over 3, which is n. And so the definite integral will be approximately delta x over 2 times f, which is my generic way of saying square root of 1 plus x squared, starting at 0. Then since it's trapezoids, then we double all of the interior ones. And we're going to move over 1/3 because delta x is 1/3 from 0, puts us at 1/3. Then, again, we're doubling because it's Simpsons. Double all the interior ones. 1/3 plus 1/3 is 2/3. 2/3 plus 1/3 is 1. That's our ending point, so we don't double the last one. It's used only once. And if you did that calculation, you would end up getting a number that is approximately 1.154. Now, I will tell you, if you know how to make your calculator do the integral, it's going to be with n being very close to infinitely many. And if you're trying to do that to sort of go around, do an end around run, and kind of finesse the system, this answer that you're going to get with trapezoids is not going to be close enough to the exact answer your calculator can. Well, it's an approximate answer too, it just has a very big n. But I'm going to call it exact just for the sake of argument. It won't be close enough to it so that you could type in the exact and get credit. You're going to actually have to do this calculation and not try to finesse it and do an end around run because, well, you won't get it right. So, just saying. Okay. What that means is that if our error is at most 0.01, that means that the actual answer that we would get for this, and this is kind of an interesting byplay of this, is that you can now say for sure that the exact answer for this lies somewhere between our approximation that we just found plus 0.01, because it could be, you know, on the high side, or it could be something that's our answer as low as our answer, as low as our answer minus 0.01, because we could be under or overestimating, and the furthest we can get away is 0.01. And so that would mean that our answer for sure is somewhere between 1.144 and 1.164. So the actual answer is somewhere between those two extremes. Those are bounds on what the answer could be according to what we just done with 3 trapezoids. The correct answer will lie somewhere between those two if we want the error to be less than or equal to 0.01. Okay, so that ends this lesson. I will see you in class.